Okay, guys, I'm on here. Will someone turn the can lights off?
So I'm going to share my screen by sharing my iPad. So that will just take me one moment to set up. So hopefully you now see the iPad, and I'm going to go ahead and start the PowerPoint from the beginning. So yes, I'm going to talk a little bit about Coulomb's law and the structure of atoms. And I'm very happy to be here this morning working with students and teachers from the great state of Kentucky. I understand from Mr. Akampura that there might be a little bit of snow in parts of Kentucky this morning. So congratulations on that. It's not here in Oklahoma. So I wanted to start out our conversation about Coulomb's law and atomic structure with an image from a portion of the equation page on the AP chemistry exam that relates to atomic structure. And I think you can see on the left, right below the words atomic structure, are two mathematical relationships, two very important relationships that on the face of it look pretty straightforward. E stands for energy. H, as is shown on the right portion of that equation column, is Planck's constant, and has a value of 6.626 times 10 to the minus 34 joule seconds. And as we'll talk about in a moment, I think it's important to understand that Planck's constant does not include the unit mole. It just has joule second. And nu, frequency, which is there above Planck's constant, is that other variable in that equation. And then below E equals h nu is c, the speed of light, is equal to lambda, the Greek letter for wavelength, and nu, again, for frequency. And we've got the value for the speed of light in meters per second on the equation page. So you don't have to memorize any of these numbers. I mean, they are available to you. But as I like to tell my students, if you haven't memorized them, you haven't done enough problems. So, so do lots of problems, and then Planck's constant and Avogadro's number, the speed of light will be easily accessible in your memory. So those are those equations for atomic structure that we have. So what I thought we would do is we would go ahead and start working on a problem that is very common for, is that showing up? No, it's already gone. Yeah, Lou had did that writing, and so he erased his stuff. So here's a typical sample problem that in the upper atmosphere, ozone molecules decompose as they absorb ultraviolet UV radiation, as shown by the equation below. And ozone serves to block harmful ultraviolet radiation that comes from the sun. And so we've got a chemical equation which says that ozone gas in the presence of ultraviolet light can absorb some of that light and actually break a bond, an oxygen-oxygen bond, to form O2 gas and an oxygen atom. And so when we typically look at this equation, we think in terms of moles, the chemical equation. But we've got to be a little bit careful with that in this particular case. And so we are told that a molecule of ozone absorbs a photon with a frequency of 1 × 10⁻⁵ seconds to the -1. And so we're then asked how much energy in joules does the ozone molecule absorb per photon. And so we're given a frequency, we're being asked for an energy in joules for a single photon. And so we're just looking, let me go back. I think I can go back on my little, now it's only going forward on my little PowerPoint. So that's kind of irritating. So let me go back here to our equation, E equals h nu, that, yeah, I want to draw. And so I'm going to go with orange. I hope that doesn't offend anybody. And so we're going to look at this equation to calculate the energy of that photon. So I'm going to jump back to just the A portion of this problem. And we are given that E equals h nu. And so this is a fairly straightforward substitution. We were given that Planck's constant was 6.626 times 10 to the -34 joule seconds. And that frequency, 1 × 10 to the 15th seconds to the -1. And so when we sort of complete that calculation, we're going to get a value, and it's pretty straightforward in this particular case, times 6.6 times 10 to the -19 joules, because we see our seconds are going to cancel. Now, this is a very small number, but this represents the energy of a photon, of 1 photon of light that can be absorbed by a single ozone molecule. Now, we're not told whether this amount of energy is capable of breaking that oxygen-oxygen bond, but, and this is what's important about that E equals h nu, that since it doesn't have the word mole in it, we have to think about the fact that a single photon of light with the frequency of 1 × 10 to the 15 seconds to the -1 has an energy that's equivalent to 6.626 times 10 to the -19 joules, which is a pretty small number. Well, if we now go to part B of this, and again, as Mr. Akampura indicated, any questions, that just chime in or put something in the chat, and that information will be communicated to me. So in part B, we're told that the minimum energy needed to break an oxygen-oxygen bond in ozone is 387 kilojoules per mole. And so the problem now is, does a photon with a frequency of 1 × 10 to the 15th seconds to the -1 have enough energy to break this bond? And we're to support this answer with a calculation. So from part A, we had that the energy of the photon with this frequency was 6.626 times 10 to the minus 19 joules. And that was for one photon. Well, if we're supposed to get kilojoules per mole, there are the units of the energy that will break an oxygen-oxygen bond. What we need to do is do just a few conversions. So if I convert, and I need moles in the denominator, and I remember in that atomic structure, the portion of the equation page, that Avogadro's number was 6.02 times 10 to the 23rd photons in 1 mole of photons. That I can now, my photons will cancel out. I'll get mole of photons in joules, and we're supposed to do this in kilojoules. And so, as I recall, 1,000 joules is 1 kilojoule. And so there's a couple of things. Remember Avogadro's number, 6.02 times 10 to the 23rd, that's a count, it's a number for what a mole is. But the units, the conversion from joules to kilojoules is a conversion that we have to know. And again, doing lots of problems where we have to do from joules to kilojoules or grams to kilograms are very useful practice for us to remember, because as you might imagine on the AP exam, there are more than a few students who will write down on that conversion, or at least the numbers that they get suggest that they've made the mistake of indicating that 1,000 kilojoules is equivalent to 1 joule. So don't fall into that little trap when you do these kinds of conversions. But when I do this calculation, I'm going to end up with a number, and maybe some of you have already figured this out, 3.99 times 10 to the second kilojoules per mole. So that photon of light with a frequency of 1 times 10 to the 15th translates to, if I have a mole of those photons interacting with a mole of oxygen molecules, that's equivalent to essentially 399 or 400 kilojoules per mole of energy. And so the question is, does a photon of that frequency have enough energy to break this bond? So what do you think? Is that a yes or a no? 387 kilojoules per mole are required. We have enough energy in this particular photon equivalent to almost 400 kilojoules per mole. So yes, we do have sufficient energy to break that bond in a molecule of oxygen. So again, any questions? And you can see this kind of a problem on the AP exam. They're not going to give us any, they're not going to tell us that we're supposed to use E equals h nu, but based upon our familiarity with the kind of information that we're given in this problem, given frequency, we're asked to calculate an energy, then Planck's equation, E equals h nu, is something that comes to our mind immediately. Okay. So I showed you equations associated with atomic structure that are provided on the AP exam, but there's also some equations and equalities of units that are not provided on the AP exam, which, based upon our experience as readers, we like to share with students to sort of, you should have this kind of information available to yourself, because we have seen questions on the AP exam that student expectation is you should know these kinds of relationships. So the fact that 1 meter is 1 times 10 to the 9 nanometers. Remember my mention of wavelength, a not infrequent kind of problem that we might get asked on the AP exam is that we might have been asked to calculate the wavelength of a photon of light with a frequency of 1 times 10 to the 15th centimeters, or seconds, to the -1. And often we're asked to calculate that in nanometers. And that's been asked before. And it would be frustrating to be able to do that calculation properly, but then forget the conversion between meters and nanometers, because the speed of light is in meters per second. And so we'll calculate with frequency seconds to the -1, we're going to come up with meters as our wavelength, but in the past, the AP exam has asked for nanometers. So we've got to be able to do that conversion easily. The next relationship, effective nuclear charge, which is you're given just Z effective. And I put in parentheses which electron, because it's very, very important that we remember that an effective nuclear charge is the attraction to the nucleus that an electron experiences. Very often students will say, oh, well, sodium has an effective nuclear charge of +1. Well, we probably shouldn't say it that way, because when we do talk about an effective nuclear charge, we have to identify the electron whose effective nuclear charge we're asking about. But that effective nuclear charge is equal to the number of protons in the nucleus minus the inner core electrons. And then the final relationship is the relative weighted average atomic mass, which I like to call the relative weighted average atomic mass, also known as the RWAM, is the summation of the isotopic masses times the fractional abundance. And so those kinds of ideas are also important when we look at mass spectra. So those are relationships that do not appear on the AP exam equation page that we recommend that you have in mind in preparation for the AP exam.
John? Professor Gelder, sir?
Yes.
Can you go back a slide? Is that possible?
Yes, I can.
I'd like if you can just speak a little bit about what you say here. I'm trying to do this from my new laptop. When you say which electron, and let's use sodium as an example. A sodium atom would have a nucleus with 11 protons.
That's correct.
And I'm going to make a very, very schematic picture here. And hopefully our students know about electronic structure. So we've got 2 electrons in that first shell. And then 8 electrons, 5, 6, oops, I lost my stylus here, come on. I apologize, there we go. One electron out here. One electron out here in the third shell. And so the effective nuclear charge seen by this electron would be very, very different than the effective nuclear charge seen by this electron. And you know, when you're talking about, and the electron-electron repulsion becomes important. So you are probably going to, or maybe talking about ionization energies and trends in atomic structure and radii, but that's where this is going to become important. So pardon me for interrupting. I think
Oh.
that's great that students understand that.
That's a good point to make, Lou, and
Z
so thank you for
effective
that representation, because
equals 1.
that's right, or
Z
that,
effective equals 11.
right, exactly.
And this is a very approximate because we're neglecting the S and P orbital. So
Right.
Z effective here would be 11 minus 2, which would be roughly 9.
Right. So, yes.
Okay, thank you.
So I'm going to go now to a picture, and Lou's going to erase.
I'm trying to clear my drawings. There we go.
So what I'd like to do now is for us to sort of consider this particular question and sort of ask you, what do you see? But in this question, we're asked to compare the relative energy necessary to separate positive and negative electrical charges. And we're supposed to compare A and B first, and then compare A and C. So, Lou might be able to put up a little poll for asking about, when we compare A and B, does A require more energy, or does B require more energy to separate those electrical charges? And we'll get some sense, some feedback from all of you about what your thought is for which case, A or B, do you think would require more energy to separate the charges?
So you're comparing just A and B.
Yep.
And we might think about the relationship between the ionization energy for a hydrogen atom and the second ionization energy for a helium atom, or even the first ionization energy for a helium atom. Okay, I'll give you guys about 5 more seconds to weigh in. And teachers, don't be shy about voting as well. I know there are several of our teachers are out there.
Yeah.
Okay, I'm going to end the polling here. And
so this is interesting, that 90% of those who responded correctly in their choice of B, that in the case of B. And so let's think a little bit about what was being asked. And when we look at the choices A and B, there's something about those choices that is the same, and something about those choices which is different. And so can anybody, if you would like to put something in the chat, to offer what appears to you when you look at just A and B little models, what might be the same and what might be different, because you've absolutely got the correct expectation that in B it will require more energy. But what the same is the distance between the charges, the electrical charges in both A and B. And what's different is the magnitude of the charge in the case of B. Now, I've just called these electrical charges, but since we're chemists and we know that things that have a positive charge or a negative charge, it could be ions, a cation and an anion. But in this particular case, I was trying to model sort of a nucleus and an electron. So when we think about the the separation between the electron and the nucleus, we think about distance and we think about charge. So let's now consider comparing A and C. And Lou can sort of clear the poll, and we'll ask, but we'll do probably, I guess you have to do, so you can pick A if you believe A has the greater energy to separate charges, or pick C if you think that C would require the greater amount of energy to separate charges. And again, we'll talk a little bit about what's the same and what's different about these two little models. So that was quick. We've got 10 responses again, and again, 11 responses. Sweet.
Someone snuck in there right at the end.
All right. So I agree with 82% of you in that choice A, that would require the greatest amount of energy. What's the same in this particular case are the charges on the nucleus and the charge on the electron, but what's different now is the distance. And what you're showing, what you're saying in this particular case in terms of that distance, that right, that we've got a direct relationship between that energy and an inverse relationship with distance. The shorter the distance, the greater the energy. The higher the charge on the cation or the anion, the greater the energy. And that essentially, just by looking at these little choices, this model, that 80–90% of you all have invented sort of Coulomb's law, which doesn't, interestingly enough, doesn't appear on the equation page of the AP exam, yet it is riddled through the curriculum that the College Board gives to the AP chemistry teacher. And so Coulomb's law, this relationship that Lou's got written on the screen, is very important. However, you will not be expected to do a calculation, but you are expected to have this qualitative idea that the energy required to separate is directly proportional to the charges and inversely proportional to the distance between the charges. So to sort of drive home a couple of questions that reflect our application of Coulomb's law, in the absence of the College Board telling us we're supposed to use the Coulomb's law, let's look at a couple of questions. First of all, I'll just quickly go to the next slide. And Lou is using, in his little equation, used U as the symbol for energy, and I just wrote out energy. So let's look at this particular question to sort of, which is an application of Coulomb's law. And I'll give you a moment to go ahead and read that. And if you'd like, Lou has got the poll up. You just have 4 choices. And why don't you go ahead and see if you can, thinking in terms of Coulomb's law, answer this question. Was that your dog voting, Lou?
That was. Jeez.
I should have started my little timer for 90 seconds.
We're about a minute. There's a timer. Can you see the poll, John? We're at 80 seconds right now. So I'll stop in 5 seconds. We've only got 6 responses though, so you should not be shy. And I'm going to stop the polling in 3, 2, 1. So I think that students should be expected to be able to answer multiple choice questions in about 90 seconds. There are on the exam.
Right.
So that's where we're looking at. And John, if you'll talk about the distractors here as well.
Yes,
it looks
I
like
shall.
most of the students who answered chose choice A.
So, right. And 83% of you who picked choice A, that is the correct answer. So let's talk just for a moment about this, because what we're being asked, and we should sort of imagine in our own minds, and I'm just going to put a zinc ion up here first, interacting with a water molecule, because the zinc is a positive charge, we know that the water molecule is a polar molecule and has a partial negative charge on the oxygen and partial positive charges on the hydrogen. And so there is going to be our Coulombic interaction.
And this is a diagram that students would be expected to reproduce on a free response question.
Yes,
So,
yes, we would want you, and have asked these kinds of questions before, to orient a water molecule about a particular ion. And so this is sort of what we're trying to think, and you can see that calcium and barium have higher radii, ionic radii, compared to zinc. And so again, what's same about those 3 ions is they all have the same +2 charge, but what's different is their relative distance. And so we should be thinking that, oh, the shorter the distance, the greater the attraction. So we want to see the attraction going in this way, that the attraction of zinc is the highest to a water molecule, compared to then calcium and then barium, the exact order of their ionic radii. Now, one of the choice B, which did get a few votes, has the correct energy order, relative strength, but the explanation for that ordering, while it is attractive, really, when we've only talked about electronegativity in class, I don't think any teachers have been talking about the electronegativity of ions. Electronegativity is usually a term that we associate with the covalent, the attraction that an atom experiences for the electrons in a covalent bond. And so we're thinking about ions and being attracted to water. And so while electronegativity is a concept that we're familiar with, and we do have this sense that smaller atoms have higher electronegativities, we don't talk about it in AP chemistry in the context of ions. So that was sort of a tricky distractor. Part C, the larger ions have more polarizability or more polarizable, which is also true. But in this particular case, the reference is to an ion dipole interaction. Largeness, again, because the distance is in the denominator, is an inverse relationship. So largeness is associated with weakness, not with strength. And again, we've got the electronegativity concept associated with ions in part B. So again, we're not told to use Coulomb's law, but again, in the information that we're provided, we're talking about the level of attraction of of a cation in water, which we know to be polar. And so it has a permanent dipole, a permanent asymmetry in electron charge. And so we think about those partial negatives and partial positives. What I'm going to do is I'm going to skip maybe the next problem in the interest of time, and I'm going to jump down to sort of our next sort of place that I wanted to talk about when we think about atomic structure, and that is a technique called PES, which is photoelectron spectroscopy, which is a technique, an experimental technique that we use to measure the binding energy of electrons in an atom. And an experiment is sort of described in that second paragraph, where we shoot photoelectrons at atoms. And oh, that was cool.
Do you have 22,000 unread emails?
Good.
That could be.
I thought I was bad.
That would keep you up at night.
There are lots of things keeping me up at night.
Yeah, right. It does, worrying about all the people that want my attention. So anyway, so this PES, and what I wanted to do is let's look at a PES spectrum, because I wanted to ask you a few questions about the PES spectrum to ask us, sort of get some sense of what information a PES spectrum provides us with. And so I would ask you, what is on the y-axis? And this is, I think, an exercise we should all go through whenever we're faced with a graph of information on an AP exam, is to look what's on the x-axis, look what's on the y-axis, so we sort of can become comfortable with the information that we're being given. And I think you can see on the y-axis, we have relative number of electrons, but interestingly, they don't tell us what each line represents. And so, so our ability to understand what's going on in a PES in a spectrum like this enables us to sort of get a clear sense of what the numbers should be on the y-axis that we're not being given. On the x-axis, we should notice the term binding energy. This is the energy required to remove one electron from an atom, and it has units of MJs, and MJ is megajoules per mole. So this is a lot of energy. And I think that many of you might be looking at this x-axis and wondering, the numbering system is a little weird. And this we associate with the strangeness of physical chemists, in that normally on the far left is the lowest is 0, and positive numbers increase going to the right. But that's not the case in PES spectra. And so we just have to be aware of that. So we can see here's 0 megajoules per mole way over here on the right. We see 3 peaks. And so what I thought I would do would ask you a few questions, and Lou can sort of set up the poll again, and we'll sort of figure out how comfortable some of you are feeling about PES. So I'm asking which peak, A, B, or C, requires the largest amount of energy to remove an electron?
And this is a pretty quick one, so I'm going to give you about 30 seconds, which is 5 more seconds than you've already taken. So we're getting quite a few responses here. 3. Okay.
All right, good. So, right, that binding energy is the measure of the amount of energy. So about 39 megajoules per mole is considerably more energy to remove electrons from peak A compared to peak C, which is somewhere around 2 megajoules.
Now, if we were talking about what is the energy, John, I think those would mostly be, we would conventionally call those negative numbers. So if you said, what's the energy of the electron in this atom, we would call it negative 39 kilojoules per mole. So this is a little bit of where you have to kind of keep in mind, does it require energy, or does it, you know, is the energy positive or greater than 0? Same with bond energies. You know, when we call it a bond energy, that's really a bond dissociation energy. So I don't know if you want to emphasize that point.
I am going to ask that question here in just a few minutes.
Uh-oh, I'm sorry, did I?
No, that's good. Everybody should have been listening, so they will have, maybe the question that I asked won't be as difficult as I thought. So how about this question? Which peak, A, B, or C, represents 2s electrons?
Relaunching the poll. And again, this should be a pretty quick question for you AP Chem students, so I'm going to give you about 10 more seconds to think about it. And then end the polling here in 3, 2, 1.
Okay. All right. A job well done out there. So I agree. B would be the 2s electrons. And so your ability as students to recognize when you were looking at a PES spectrum that the numbers on the y-axis are, let's see, I guess I had my eraser. 1, this is 2, and this is 3. So each of those lines just represent 1 electron. And what it's there. So that this A peak, that's our 1s, our B peak is our 2s, and then the C peak is the 2p subshells. And the height of each of those peaks denote the number of electrons who have that energy in the atom. And so the PES is our experimental evidence for the existence of subshells. That is, that when we look at that second shell, peaks B and C, we see, interestingly, that not all electrons in the second shell have the same energy. So that's really cool. So let's try another question. So
John,
here,
there's a question in the chat box that's asking what the term I lost it. The term binding energy refers. What do we mean by the binding energy? And maybe a cartoon of an atom would be a good thing. I can draw one up there, or you'll get your stylus.
I'm going to jump all the way down here. I'm going to give you a different representation for the particular element we have been looking at. This is a representation which we frequently refer to as an energy level diagram. And the binding energy, you can see on the y-axis of this little graph, here is energy. But down here, here we can see the 1s energy, but up here near the top is the energy is equal to 0. And so as Mr. Akampura was saying, oh, if the energy is 0 way up here at the top of this little diagram, then the energy's going going down, these are all negative energies. And so when we talk about the binding energy, we're talking about the energy that's required to remove an electron from the 1s, the 2s, or the 2p level. And so we can see that the distance to zero energy for the 2p is that sort of distance, and here for the 1s is this amount of energy. So the question becomes, well, which of those energies, which electron, an electron from a 2p subshell or an electron from a 1s subshell requires more energy to remove? And I think you can see with this kind of a representation that the binding energy is this positive energy that's required to remove the electron. So here's the binding energy for that 1s electron. Here's the binding energy for the 2p electron. So binding energy is just this positive energy that the atom has to absorb with a photoelectron to remove that particular electron. And we call that energy the binding energy.
You're welcome, Hadel.
So hopefully that little explanation has helped a little bit. So now let's go back to this other question that we have about this particular spectrum. Which peaks, A, B, B and C, or C? So this will be choice A, this will be choice B, this will be choice C, and this would be choice D on Mr. Akampuro's poll represents the valence electrons for this particular atom. Which peak or peaks? Which peak or peaks represent or represents the valence electrons for this atom?
Okay, we'll take about 10 more seconds. I feel like I'm hosting a call-in show. We have Mildred from Des Moines who wants to chime in on this. 3, 2, 1, okay.
So valence electrons are electrons in the outermost, and this last word is the most important one because we see so often on the AP exams students misinterpreting the valence electrons. But valence electrons are electrons in the outermost shell. So the correct choice would be C, because it is both the electrons under peak B and under peak C that represent the electrons in the second shell. And again, in a PES spectrum that we see on an exam question, information about the shells aren't revealed to us explicitly. That information is there because in a PES spectrum, we can usually identify shells by groupings of peaks. The proximity of peaks to each other gives us a suggestion of the number of shells that might be in a PES spectrum. So clearly A electrons and the BC electrons are well separated in terms of energy from each other, but the B and the C are very close to each other. And so choice C is the correct answer, that those 5 electrons are the valence electrons in this particular case.
John, if you'll just, I have 2 questions here. One or 2 comments. Why is that important? And you're talking about bonding. And also, do you want to mention transition metal and transition metal ions? Because that's a place where students do get, confused quite a bit.
Right.
Or do we want to just stop?
Okay, so remember that sort of our knowledge of valence electrons helps us in many different aspects of our chemistry. It gives us an idea of maybe, in the case of metals, how many electrons are likely to be lost to form a cation. And for those non-metals on the far right, how many electrons they might gain to form a negative charge. And for those elements, those non-metals that are sort of in between, the valence electrons can give us a suggestion of how many electrons or how many bonds they might form. So oxygen, for example, who has 6 valence electrons only needs 2 more. And so O2 minus is a very common charge for an oxygen ion. But oxygen also likes to form 2 bonds when it forms covalent bonds. So valence electrons are important in that regard. When we think about transition metal and transition metal ions, this concept of valence electrons gets a little bit muddier. And at least in my classroom, I stay away from that sort of terminology when talking about transition metals. But I do apply it for the main group, for the group 1 and 2 and group, 14 through 18 in the modern periodic table. Yeah, 13 through 18. Okay, so let's jump to this last question that I've got. Which peak, A, B, or C, represent electrons in the lowest energy level?
Not to have a spoiler here, but if you're asking for the lowest, it's pretty much going to eliminate the one in the middle.
And those Kentucky students, they've got that figured out.
Yes, they do. Okay, I'm going to end the polling in about 3 more seconds here. There we go.
All right. So good. That little bit earlier conversation that we had, this PES spectrum, which has got binding energies on the x-axis, is sort of, that binding energy is the energy required to remove. And so, but when we look at an energy level diagram, we can see that those 1s electrons are at the lowest energy, and therefore would require the most energy to remove one of those electrons. And so it's, the term energy, when it's associated with an electron, we can talk about binding energies, we can talk about the energy of the electron in an atom. And so it can be a little bit confusing. And so we've got to be able to, when we think about PES spectra, we should want to sort of have this image of an energy level diagram, which I think many of you are familiar with in terms of, when we are writing electron configurations. That according to Aufbau's rule, we got to start with the electrons in the lowest energies first and then increase them. And so as we write electron configurations, we know that 2p electrons are higher in energy than 1s electrons.
And as we
so,
look at that, well,
go ahead.
I was going to say, we want to be careful, John. I know in the interest of space, but you haven't labeled the 3s and the 3p and the
Right.
And also remember that that as you go up, the 3ds will be higher than the 3p and higher than the 3s, but also the 3d will be higher than the 4s. And you want to look, as you look at the periodic table, that's a pretty good hint. So we're going to have a few more minutes here. So why don't we close up
so I'll just real quick, what I wanted to show was that there is a link on one of the slides of the PowerPoint that, and I think in the PDF, I've written out that link for the teachers, but here we can sort of look at what happens to the energies of these different shells as we add electrons. And so this little movie is included, a link to this movie is included in the PowerPoint slide.
I like that.
That I had sent out. And also, Lou, there is a link to a set of TES spectra that teachers or students can look at. So you could add, sort of pick from the little abbreviated periodic table some PES spectra, and you can sort of see that as you go from lithium to beryllium to boron to carbon, look at what happens to those 1s electrons. So, so very, just wanted to point that out quickly in the PowerPoint.
Right, and just to tie this around to what we spoke of earlier, so the 1s electrons are not shielded. So for them, the effective nuclear charge is the nuclear charge, and they monotonically have greater binding energies, which you've now called ionization energies, but we just want to emphasize that represents the same thing as the binding energies.
Yeah.
And you've got a logarithmic scale here, which I'm noticing.
Yeah. So
students should be expected to be able to interpret those. Terrific.
Right.
That's I'm going to play with that. Absolutely.
So, so anyway, I think that we're down. Am I supposed to only babble for approximately 60 minutes, or do you want
this is well, any time that you spend, we're going to take away from Ms. McGaw. So let's let's take a 5-minute break here. I'm going to pause the recording, and we'll take about a 5-minute break, and then we'll pick it back up. So thank you so much.
Thank you, students from Kentucky.
Okay, so welcome, you guys. Now we're going to need your calculator. So if you, my name is Lisa McGaw, by the way, John's partner. So anyway, grab your calculator. A periodic table would also be handy if you have one near. Something to write with or on, because I really would like for you to do some problem solving since we're talking about stoichiometry in the mole. That's probably like your best friend, like Lou said. It is your best friend in AP Chem. And just like Gelder said, you know, the AP equation sheet does give you a lot of formulas, and you'll get these formulas even when you are in multiple choice or free response. But some parts that you might want to like make sure that you, you know, what has to do with a mole. Well, we might be able to use that for moles, right? PV equals nRT, that little n, we might be able to find that. Mole fraction, not really that common, but a fraction is part over whole. So if you wanted to know a mole fraction of some particular component, then it would be get everybody in moles. And then you could put moles of one component over all the moles in a component. Then you've got this little formula right here. Moles is equal to mass over molar mass. I hate that in chemistry we have so many capital M's and M's in particular, but you've got the right-hand side over here. So you've got everybody labeled out so you'll know what's what if you get confused when you get to your test. And sometimes you will because you get nervous. If we work with gas laws, you know, we always have to use that Celsius plus 273. And I guess even with density, we could get mass. If we could get mass, we could go to moles. So, and then this equation down here at the bottom of the page, molarity, moles of solute per liter of solution. They just didn't write it as an equation. So you might want to take your equation sheet and say capital M is equal to moles of solute per liter of solution and put it more in a formula kind of thing so that you have it written out for yourself. I think that might make it a little bit more handy. And then there also are some equations that are not found on the AP equation sheet that come into stoichiometry and mass, and think about lab kind of things that you might do. So percent yield or percent error, those are never given, but still ask about. And then maybe mass percent, like again, it's just a part out of a total, so that, that's not so bad. And if you're doing formulas like formula writing, empirical formula, molecular formula, my students always have a hard time remembering how to get that molecular formula. So if you'll take the weight of the empirical formula times some whole number, that usually gives you the molar mass. So you can take the molar mass of the molecular compound divided by the empirical formula mass, and you could get that. So that's kind of like just a hint to remind you about what you're supposed to do when you're doing a formula for a compound. So moles are everywhere. They're kind of like ubiquitous, right? In chemistry, they're in basically every chapter that you're going to do. So can you think of any other ways besides grams to moles, molarity times volume, the ideal gas equation, Avogadro's number? Is there any other way that you might think of coming up with moles? Anybody else have a different idea? You can chat it in the chat box, and then John can tell me. I don't see the chat when I'm doing this kind of presentation. I can think of one more. I was leaving something out on purpose, just to see if you guys are paying attention. Anybody have another one? Is anybody writing anything in the chat?
No.
Okay. What about this one? So if I have a gas at STP, that's the only time you can use that little magic number of 22.4. We see it everywhere on the AP exam. When you're going between volume and you want moles, don't use it for anything but a gas at standard temperature and pressure. But that's another way that you can actually end up going to moles. And so Mr. Akampora actually has this little symbolic to help you navigate your way around. You can't have that on your exam, but if you ever get lost while you're just solving homework problems, it's kind of helpful to know, oh, do I multiply? Do I divide? But if you put your units in, you can always figure that stuff out. All right. Yeah. And you always have to show your work for moles in order to get credit. Even when you're going to do a little technique I'm going to show you today, you still have to show your work for moles.
And Ms. McGaw,
yes.
I thought you were going to mention, because some of you may have studied electrochemistry yet, and if you haven't, you will, and you're going to find it necessary to convert from coulombs to moles of charge, and you'll use something called Faraday's constant there.
Okay, so we could say that there's 96,500 coulombs.
Which is a unit of charge that physicists came up with long before chemists even knew that atoms existed. So
yeah,
kind of came to the party late on that one.
So you might actually have to do something like that. Yeah. So if you looked at an equation, maybe an equation like, so in this equation, you have 1 mole of electrons for every 1 mole of Fe2 plus or something like that, whoever you're talking about in that particular equation. So yeah, you would actually be able to use that Faraday's constant as well. Thanks, Lou. I was thinking that doesn't come until like unit 9, so I didn't know if anybody was there, but a lot of people do that with equations and reactions in stoichiometry. Oh, so what do you think about this one? When you look at particulate diagrams, it's like, what are you talking about? So again, we have a poll. So which box represents the best answer for this reaction? A, B, C, or D? And there is a hint. Can you write the reaction? You may have to write the reaction before you ever begin. Did anybody come back from break?
No, I think that it takes a while to count things here.
Exactly.
Yeah.
90 seconds, remember?
Yeah, you do have 90
Right.
seconds. I was like, yeah, you only have 90. So yeah, you have 90 seconds.
So we're not even at a minute here, and it took me a while to count things.
I can't hear you.
I can't vote.
Yeah, I was trying to vote a minute ago on John's and I couldn't vote. So if
You're
I
a host.
unplug this, will you be able to?
Yeah, I mean, I don't need it here.
And we're just coming up on 90 seconds now, and it's looks like a pretty close race here, but I'm going to give you 5 more seconds.
5,
And
4, 3, 2.
There we go.
All right. So let's share those, lose sharing. So we've got some A's, a little bit more A's than we do B's. So let's just look at this. First, we have to write a reaction. So in these particle diagrams, hopefully there will always be a key so that you know what you're talking about. So if I put X2 plus Y2, and these are gases, and you can tell that because they fill the entire container. So I'm going to go ahead and say gas. You do not have to write phases when you're on an AP exam, but it's always kind of handy. And then if you look in most of the boxes, A, B, and C, you see a product that has a dark circle and 3 light circles. So that product would be YX3 or XY3. We have no idea, right? We don't know if it's, we don't know who's the cation or the anion, or if, since it's all gases, it's, no telling what it is, but that's okay. Is that equation balanced? And it's not. So if that equation is not balanced, you need to balance that equation. So when I balance that equation and put in my coefficients, I'm going to put a 2 in front of YX3. And then I'm going to put a 3 in front of X2. And so now I have a balanced chemical equation. And what I'm going to do is I'm just going to count what I have. I have 3 dark circles. Those are my Y's. So I'm initially starting with 3 of those. I'm starting with no product. And I'm starting with 1, 2, 3, 4, 5, 6 X2s. So, oh my goodness, this is a limiting reactant problem. Yep, everything basically is going to be a limiting reactant problem, right? We're going to have those all the way throughout chemistry. So for every 1 Y2, I need 3 times as much X. Do I have 3 times as much X? I have 3 Y2s. Do I have 3 times as much? I don't. So this X2 is going to be my limiting reactant. I really would need 9, but I only have 6. So all 6 of those are going to be used, and I'm going to be left with 0. So if I only have 6, now let's work backwards from, let's work backwards. So we're going to work backwards here. So for every 3, I need 1. So for every 6, I'm going to need a third of that. That means I'm going to use 2 of those and have 1 left over of Y2. And then let's look at this ratio. For every 1 Y2, you can make twice as many YX3s. That means you could actually make 4 of those and you would have 4. So if I find a box that looks like this with 0 of the colorless spheres, 1 dark sphere and 4, oh, look at that, it's choice A. So does that kind of make sense? So what I just did with you is this little idea of solving problems using what I call a rice table. For a reaction, initial number of moles, what actually reacts, which really, this is going to my coefficients in the balanced equation, and then E, the ending number of moles. I use those same letters in equilibrium, but when you're probably about ready to start equilibrium, but in equilibrium, I use molarity. That's what we do. And so this is a limiting reactant problem in stoichiometry. So let's try another one of those. So here's what the little acronym actually means. So you've got it down. And consider this problem, all right? So consider this problem right here. I've got to close that poll so I can see a little bit better. So if you start with, this is just like the Bunsen burner that you probably haven't gotten to touch this year, but methane gas comes out of the burner, burns, makes carbon dioxide and water. And so it says if you just had 1.5 moles of methane and you have 1.8 moles of oxygen, assume there's no carbon dioxide, which table makes sense? So what I have for you is two tables already set up, and I'm going to label these tables A and B, and Lou's going to put up a poll, and I want you to tell me which table makes more sense, table A or table B. Yay, one vote. It's a lot of numbers to look at.
And again, Lisa, I think it's important that students realize we do this in moles because these formulas and equations represent numbers of particles, not masses or volumes.
That's right.
So, you might be given the grams or you might be given milliliters, but almost always the first thing you're going to need to do is convert to a number of moles, because in chemistry, things happen in ratios of numbers of particles, not necessarily in ratios of numbers of grams or milliliters.
I always like to think of it like, you go get a dozen eggs, a dozen means 12. And then I could go get a dozen donuts, and a dozen means 12, but my donuts do not weigh the same as my eggs weigh, even though I have 12 of each. So it's the same here. We have Avogadro's number of things, but they don't mass out the same. The only thing is that equivalency is that mole. All right.
We're coming up on 90 seconds, so I'm going to end the polling here.
Okay, awesome. And I like that too. 75% of you said table B makes more sense. Would anybody like to open up your mic and just say why that makes more sense, or why table A to you didn't make any sense? Would anybody like to share? Chat it in the chat box.
Honestly, the numbers didn't make sense in A. And so just the -1.5 and the -3, that didn't, I mean, I know that it's 1 to 2 and I get that, but the numbers don't make sense until you get to table B. That's just
because what didn't make sense about that table A. I like exactly what you're saying. Because if I had 1.5 moles, I would need 3 moles, right?
right, but I don't have 3 moles. I only have 1.8. So
Correct.
yeah.
Yeah, exactly. And that's what was kind of giving it away. It's like you can't come up with a negative number of an amount of moles. So that didn't make any sense at all. So you've got to think about which one was the limiting reactant. So that's kind of how that little table works. And I like it. I especially like it for working multiple choice questions. So if you kind of set this one up in the same format, like if you were to do this on your AP exam, write on your multiple choice. Do not hesitate to write. You've got to when it comes to some of these math problems. And I think, Lou, did they say for math, it was about how many, what was the percent of mathematical kind of problems? I want to say 40-something% of the multiple choice actually had to do with math. They don't always have a calculation, but they have something to do with math. So if I were to do this on my test, I would put a 1 here, and I would say, okay, 5 moles of NaOH, and I would have 0 of my product to begin with. And I say, okay, for every 2, I need 6. I only have 1, so I would need 3. Do I have 3? I have more than enough. So this is going to be excess. This is going to be my limiting reagent. So I'm going to use all of this 1 and be left with none. You don't always have to go through the whole problem to figure out what you're looking for, because here we're looking for how many moles of H2. Once we find out this C row tells me my coefficients. Now I can say, okay, so for every 2, I can make 3, but I only have 1. So how much could I make if I were just going to have Sorry, I'm like that's kind of crazy. Somebody's not so good, right, at this. So how would I figure that out? Oh, that's very complicated. Well, let me do something easier. So for every 2, I can make 6. If I only have 1, I could make 3 times as much, which would be how much? That would be 3. So I'm going to use 3 of those. Oh, now this is pretty easy ratio, 6 to 3. It's half of that. I can make hydrogen at half the amount that I'm going to use up the sodium hydroxide. Well, what's half of 3? That's 1.5. And so I have my answer fairly quickly. Any questions on how you do something like that? I use this technique going through those multiple choice questions all the time when they're released. I sit down and I start working them that way because I don't have to do long dimensional analysis when sometimes that math is just going to ache my head and I want to be able to do it fast. So let's see if you can do this one. All right. See if you can come up with the answer to this one. Try that little technique. Lou will put up a poll and see how you do. How you doing? So a couple more people. I sort of have it set up for you a little bit. I just didn't finish it completely all the way out. Okay, so that's like 90 seconds. So only 6 of you voted that time, but all 6 of you chose answer D, and that would be exactly the right answer. So for those of you who didn't answer this one, sometimes you do want to skip the math because it takes a little bit of time, but if you try to set it up, it's not so bad. So let's just look at this. For every 2 potassiums, you make only 1 hydrogen. So if you're going to use 0.4 potassiums, half of that is going to be 0.2. So you're going to end up making 0.2 moles of hydrogen, but they wanted to know at STP how much volume, so how many liters. So 0.2 moles times 22.4 liters per mole, and you would need to set that up to get your points there. And then you say, well, that's pretty easy because 2 times 22.4 would be 44.8, but this is a decimal. So 4.48 liters. And so you can figure out the math. Usually it comes out pretty easy. The math, the numbers aren't supposed to be hard. We don't get a calculator for the multiple choice. And so that's kind of a pain, right? So let's try another problem kind of the similar way, but this time, this is going to be one of those free response kind of questions. All right. So the same kind of thing we could do. And I just took a piece of this problem. So you know that this is not a whole free response. I just took out the part that we might need. So the first thing, as we read through a problem, and when you read through a problem and you're looking at this, always underline, highlight your text, interact with it so you don't have to read it again. You don't need to do that. So we have carbon tetrachloride can be synthesized. Okay, big word. So when you're going through these problems, don't let those words confuse you. Synthesize means to create, make. You see this as a product over here. And so CCl4 is produced, synthesized. Sometimes the AP test uses words that we're not all familiar with, but that's all that that means. According to the reaction, a chemist runs the reaction at constant temperature of 120 in a rigid 25-liter container. That means the container can't change its size. If it's a rigid container, it's going to be 25 liters. And so we know a temperature, we know a volume. Chlorine gas is initially present in the container at a pressure of 0.4. All right, so now we have a pressure for chlorine gas that initially starts at 0.4 atmospheres. The first question to us is how many moles of Cl2 are in the container? Is there an equation from the equation sheet or one that you can think of that connects pressure, volume, and temperature? And you're thinking in your head, I bet, yes, you are thinking N is equal to PV divided by RT. You don't have to rearrange your equations. I like to rearrange my equation just because it makes it a little bit easier. So the pressure is 0.4 atmospheres. The volume is given as 25 liters. Let's talk about that R value in just a second. But one thing we know we're going to have to do somewhere else on our page is we're going to have to change the temperature from Celsius to Kelvin. So we're going to go ahead and add 273. And so that will give me 393 K. So I want us to go back all the way over to this equation page. Look at all the values that we have for R. We have 3 different values. Sometimes in the angst of the exam, students often just take the first value for R. We see that so often. But what's wrong with that is the units don't match the problem that I'm solving at this very moment in time. I had a pressure in atmospheres. So I would like to take the second value of R. Just be careful about that because we see that happen over and over, because if students don't put units, they leave all their numbers naked, which is never very comfortable, right? So don't leave naked numbers. But if you leave your numbers as naked numbers, sometimes you might make a mistake, and we don't want that to happen to you. I'm looking for this problem. Here it is. So what we're going to use is we're going to use the gas 0.0821 and liters, atmospheres over moles and Kelvin. And if you put all your units in there, everybody is going to cancel out. And so when we do that calculation, we actually end up with 0.310 moles of chlorine. So that answers part I. But then in double I, in II, the question is how many grams of carbon disulfide are needed to react completely? Oh, wait. Okay, so let me just try my little table here. CS2 plus 3 chlorine goes to CCl4 plus S2Cl2. So initially I start with nothing. I know that I'm starting with 0.310 moles. And so if I set up my table, here's what else I know. I want to end up with 0, 0 of CS2 and 0 of chlorine. It wants to completely react every bit of that away. So if I'm going to use all of this 0.310, how much CS2 am I going to have to use? For every 1 CS2, it takes 3 times as much chlorine. So I need to take this 0.310 and divide it by 3. And when I do that, I come up with like 0.103. So I must have started with 0.103 moles. Oh, wait, they didn't ask me moles. I better go back and read my problem again. They want grams. Well, the cool thing is when you find this number of moles, you can always convert it to anything that you want it to be. So if it's going to take 0.103 moles of CS2, I just need to multiply that by the molar mass of CS2, which comes out to be like 76.13 grams of CS2. And so I end up with 7.86 grams of CS2. So typically on the exam, when we're given points for this kind of thing, 1 point would be for this problem right here, just to get the moles of chlorine. And then typically I might get 2 points. I'm going to give you 1 point because you understand the ratio is 1 to 3. And then I'm going to give you another point for converting back from moles into grams. So we see this on the exam going back and forth in all different kind of directions. All right, so now your turn for another multiple choice, not really with a table, because this is a completely different kind of problem, but we still have to use moles. So this is asking for a formula of a hydrate. And if you remember, hydrates look something like that. They have some water molecules locked into their structure, and we don't know how many water molecules are here. But when I heat this up, you may have done an experiment like this or seen this on a video this year, because this would have been like in Unit 1. You would end up with some solid, and then water leaves as a vapor. As you heat it up, it leaves the system. And so sometimes just taking what's given to you and writing out a reaction might make that seem a little bit more sensible in your brain, especially when it says something like losing 54% of its mass. It's like, what? It lost 54% of its mass. So what could that mass have been? What would that mass have been there?
We're at about 90 seconds now, but this is involve a little bit of arithmetic, so we'll give folks about 30 more seconds to work on this one.
And the same thing will happen to you on your exam. You know, it says 90 minutes from each multiple choice question. However, those multiple choice questions, some are super fast, like the one that you were looking at with PES data in the earlier session. That might take you 10 seconds to answer. And then one like this might take you almost 2 minutes to answer. And so that's perfectly fine. The math ones, this is just like, since we're doing stoichiometry in the mole, all of these are kind of math based. Okay.
All right, I hope you folks are getting a little bit more comfortable with this. We're going to end the polling here and see how we did.
All right, we only have 4 votes there. So somebody's not doing all of it yet, right? So let's check this one out because it is really kind of hard. It says this compound is going to lose 54% of its mass. Well, what did it lose? It lost its water, right? So 54% of that was water. That means 46% of that must have been X2CO3. So now what I have to do when you're trying to find a formula, you have to change grams into moles, but we don't even have grams, but we kind of do because we're assuming a 100% sample would be a 100-gram sample, and that makes this problem solving way easier. So we're just going to say 46 grams of M2CO3 or X2CO3. I guess I'm changing the formula of their crazy formula, right? X2CO3, 1 mole weighs 153 grams. They told me that. I didn't have to go calculate it out anywhere. And then I have 54 grams of water. And I know that water weighs about 18 grams. You wouldn't have to get all of those digits. When you're working a multiple choice question, do not think you have to go and get every decimal point. You've just got to get in the ballpark, all right? So if I take 46 and divide by 153, it's like, oh my gosh, what do you want me to do? So look at the math and let's see if we can kind of mental math that one out. What about this one for water? If you think of 18 as being like 20, how many times could 20 go into 50? Well, it wouldn't even be 3 times, but 18 times 3 is actually 54. So you kind of, that one comes out exactly 3. So now let's go and do the same sort of thing up here. If you think about the 46 maybe being like 50, and think about the 153 being about 150, 50 over 150 would be about a third. So that would be about 0.3. What do you think about that kind of math? That's what you're going to be able to do when you're doing some of these multiple choice without my calculator. If I can know my fractions, and I kind of have to do that. But now when you're doing a formula problem, you get your grams into moles, percents go directly into grams, grams to moles with the weight off the table. And then you divide by the smallest number of moles to see what your ratio is. So it works like that for a hydrated problem. It works like that for a plain empirical formula problem. So the smallest is 0.33. And so if I'm going to divide 3 divided by 0.33, that's going to give me 10. And so it must be choice A. That was a tough problem, but I wanted to kind of go through that math with you because you will have those. And if you guys can do the math problems on the multiple choice, you will be outscoring the normal student. And you know you want to be earning about 75% of those multiple choice questions in order to score that 5, or maybe about 80% these days, I think, actually. So that's kind of your goal, to be scoring a 5 for the exam. Lou wants you to score 5s. I want you to score 5s. So any questions about that problem? Does that make sense?
So like in many things, I guess, Ms. McGaw, you would say that the key thing is to convert from mass data or even volume data to mole data and mole ratio, and look at mole ratios. And that is so important in almost every chemical question.
Yeah, but those are not easy. They take some time. So on the first initial sweep through the exam, you might leave it blank and come back to it if you have time to make sure you get it done. So here's another one, but I think it's the same type of problem. So I think I'll skip over that one for a second and see if you can do this particulate picture, very similar to what we were doing in the other problem, but it's asking you a different question. So a new poll. Another particle picture. But they give you a scenario and then ask for a brand new scenario. See if you can try to use that rice table on this one. That seems to make these particle pictures really accessible.
Do you think the first step is to come up with a balanced equation for this reaction?
Yes, you have to have a balanced equation. You cannot do it otherwise.
And you can use the particle diagram given, and there are going to be several of these particulate level diagrams on the AP exam, because it really does, assess whether students can look underneath the hood and see what these symbols really mean. And I think it makes it easier rather than trying to memorize lots of facts and formulas.
Yeah, because it's still chemistry going on. So 5 moles of HO. I don't see anybody voting. Are you guys still out there? There we go. Here comes some votes.
Could have mentioned the polling is anonymous, so we're not Your teachers
Yeah,
aren't
nobody-
giving you grades on this.
Nobody knows who you are. That's good.
Well, you didn't, you know who you are. But we don't.
I don't know if I always know who I am.
Okay, we've got 4 voting members and several non-voting members here. So I'm going to close the polling here in 5 seconds.
Okay. It's 10:40.
Here we go.
All right, so let's look at this one. Do you really have to count all of these in the initial box? Not really, okay? You don't really have to count them all. What you do have to do is you have to look and get a balanced equation. So every time you're doing stoichiometry, that is always your very first step, even if it's not given. You've got to have a balanced chemical equation. And so then you just go, okay, for every 1 A2, I need twice as much B2. If you have 5, do you have twice as much? You definitely do not. So this is my limiting reactant. You're going to lose all of those and end with 0. All right. So then if you're going to use 6 of these B2s, you're using half as much A2. You're going to use 3 A2s and be left with 2. And then you do a really easy ratio. For every 2 B2s, you can make 2 AB2s. So if you're going to use 6, you're going to make 6. And so right here is exactly what you would have at the end of your beaker. And sometimes you have to do that. So how does that look? Is that getting a little easier? Practice does make this easier. So if you haven't practiced a lot, but look what happens on your exam. Hey, why is it not wanting to change page? There it is. Look at this problem. Have you seen this one already this year? Here I have to go backwards. They want me to actually fill in the box. So I'm going to give you just a second and see if you can fill in the box. See if you can fill in the box. Try to make yourself a little bit. It's 10:43. How are we doing on time? Oh, we're not doing very fast on time. So let's just look at this one. So 2NO plus O2 goes to 2NO2. We start with none of that. So what we know here, if we're going to work backwards, we have our reaction. We don't know what our initial box looks like, but we do know what our ending box looks like. So we have 1, 2, 3, 4 NOs. We have no oxygens because that would be 2 spheres like this, right? Oxygen is diatomic. And then we made 1, 2, 3, 4 NO2s. So we're just going to work our way backwards on this. So for every 4, that means I must have gained 4 of those. I must have lost 4 of these because the ratio is 2 to 2. So if I'm going to make 4, I'm going to lose 4. Now just go back and add 4 and 4 would have made 8. And then you've got to figure out how much oxygen that took. So for this row right here, the C row is the row you're looking at because that's what goes with your coefficients. So if you used 4 NOs, that's twice what you had, right? For every 2 NOs, you're going to use up 1 oxygen. So if you've got 4, you're going to use 2 oxygens. That means you must have started with 2 oxygens. And now I can draw my picture. And so in my picture, and you guys, when you're drawing these on the AP exam as a reader, it's super easy if you will just do like, you don't have to make them all crazy. Just line them up. It makes it super easy for us to just grade them because we can count and we don't have to get lost because we can't like actually write on your paper. And so if I'm counting, and if you were to make 8 and you put all of them together like this, and then you just did your O's over here, I would be super happy with you because then I can just like immediately look at it. It takes me 10 seconds and I know that you're correct. So how does that one look? Sometimes you go backwards. What about something like this? Holy moly. And Lou already has the poll up. See what you think about this one. It's got like 3 reactants, 4 products. Really, would they ask me to do that on the exam? You bet they would. You bet they would. Start by putting your moles in. So 1 vote so far. Couple more. Okay, Lou,
Okay, I will find the button, sorry.
let's go from that one. That's got 5 votes. So let's look at this. Did you need all the information they gave to you? Not really. So sometimes there's distractor information, and this one had some distracting information right here. I don't really care how much of those 2 things I have. I didn't really need to know that. They're asking me, how much HI do I need to produce 2.5 moles of I2? What's the ratio? For every 5 I2s produced, I need to use 10 moles of HI, so I need 2 times as much. So what's 2 times as much if you're looking at this C row? If you're going to use 2.5, twice that would be the number 5, and you're done with that problem. So even laying it out without going through the entire table, sometimes that tool can just make things a little bit more clear when it looks very murky. And that one looked very murky and scary because it had so many different numbers and so many different substances. So don't let that scare you away. Here's another kind of problem that could be asked, another scary looking problem, all right? Another super scary looking problem because I have so many reactants and so many products and then different charges. We'll skip this part. Actually, I wrote the balanced equation for that earlier in this session. So let's just go to the second part of this one, and let's look at what we can do right here, even with a redox reaction. So this is a redox titration. You talked about those probably in Unit 4 when you were doing reactions. And the next time we get together, I think in February, we'll be going over more reaction writing and such. So if I do the same kind of thing here, a student titrates a 10 milliliter sample. So we're not going to put milliliters into this table. We're only going to put moles into the table of iron. They want us to know the concentration. The brackets mean concentration in molarity. So what I really want is I want the molarity of Fe2 plus. So I need to have the moles of Fe2 plus over the liters of solution. And I already know that number. So I already have my liters, or I have milliliters. So I have 0.010 liters, or you can use millimoles if you like that too. So you could use millimoles and milliliters. That's what they want me to calculate. It takes 17.48 milliliters, and the concentration is 0.0350 molar. So you're saying, okay, well, how does that fit into this table? Here's what I want you to understand is that when I reach this equivalence point, then I'm going to have 0 left of each of those reactions. Problem. What do I have to do? I have to get moles, and I have to show that mole work. So let's show that mole work right here. To get moles, we have a volume and a concentration. So if I will say molarity is equal to moles per liter, and I know that this is 0.350 molar equal X moles over 0.1748 liters, then I can calculate, just cross multiply. The volume times the concentration will give me the number of moles, and the number of moles that you get for the iron, for the MnO4 is 6.118 times 10 to the negative fourth moles. All right, so you guys, this is what we have to see for credit. You can take and just put your answer into your table. I'm going to give you 1 point for showing me the setup right there. I won't give you a point if you just give me the number. But now what we have to do is we have to figure out, well, how much iron would it take to use up all of that? Because I know I'm going to use all of this one. So how much iron is it going to take? It's going to take 5 times as much. One for every 1 permanganate ion, it takes me 5 iron 2s. So 5 times as much of that. And that number comes out to be 3.059 times 10 to the negative third. All right, well, what did that help me with? Oh, that helps me to solve the molarity, because now I have my moles, I have my volume, so 0.003059 moles divided by 0.010 liters, and I can get my molarity, and my molarity comes out to be 0.306. So sometimes when it's really confusing, start with something as simple as one of those tables. Oh, I have so many more favorite problems, you guys.
And
So
this is, sorry, Ms. McGaw, this is one where you really have to do a lot of things to just get a very few points, but those points are awfully valuable.
mm-hmm. Yes, the points are very valuable when you're writing and showing your work. So I'm going to skip this one. I'll go ahead and just give you the answer to it, though. I meant to do that with that other problem. And then you can go back after you're finished with today. I don't know. You probably will. I would think that you might want to go back and rework some of your problems again and just kind of see how fast you can move. The more practice you get, the better you're going to be. This is another type of problem where you've got moles and then you also have milliliters and molarity. So you're going to have to get moles from that volume and concentration again and see who's the limiting reactant. Super common problems for multiple choice, but with pretty easy math. So I want you to try maybe that one. And then here's a similar problem to what we just did with that oxidation reduction reaction. This is an acid-base titration neutralization reaction. And again, the initial concentration of HNO2, so we're going to have to get the volume, and we already have the concentration. And so the point is, you're going to end up with your last line. You're going to have 0 of each of those left over when you reach the equivalence point, which is happening right along here, right? So that equivalence point is happening when you're at 20 milliliters. And so I just kind of wanted you to see that, but it's exactly the same kind of problem solving that we did with that other oxidation reaction. So I'm going to skip over to this problem for our last problem. How many people have done this one already in class? Very many people have done this one. Maybe, maybe no. This is a really good problem. And I'm going to number my pieces of data here as 1, 2, 3, 4, and 5. All right. I'm going to number the data. That kind of makes this a little bit easier. And let's read through this problem and even see what the heck they're giving me. I already kind of tell that I have a mass of some tablet, some filter paper, and then filter paper drying first, second, third. Oh, this is just doing one of those gravimetric analysis kind of labs, right? So one that you probably have not really had the opportunity to do this year. So that's why I kind of wanted to look at this. All right. So I'm going to skip then this part A for right now. But we can't really skip the whole thing. We're going to need that in a minute. I may come back to it. Explain why you would dry and weigh the filter paper with the precipitate on it. Why would you do that 3 times? Like, what would be the point of doing that 3 times? Anybody put that in the chat? Why would you dry and weigh and dry and weigh and dry and weigh? What do you think somebody's trying to do?
Check for accuracy.
Judy, you're exactly right. Check for accuracy, but accuracy probably would not earn you the point because we're looking.
It says to make sure all the water is gone, otherwise
Liz, exactly correct. Like that's what we would be looking for. So watch out for some of those vague terms. When it's vague, we don't really know exactly like, well, are you hedging your bet? What are you doing? So what was going on here, drying means I'm getting rid of the water, because you see what they did is they had this beaker, they stuck this little tablet in there with their water and it started to dissolve. And so now they made a precipitate because they added in some, so they added in Ki, then they added in some lead nitrate, and then they made a solid precipitate down at the bottom. They collected that precipitate. They wanted to get dry. And so these last 2 numbers, you're trying to get within 0.001. If you get like, we call that heating to a constant mass. And then we have, for sure, we know that we've gotten that answer. So I would want to only use that very last number in any calculations that I do, because that's the only one that's decent. All right. That's the only one that's accurate to use the other word. So how about that? So is that okay so far? Now the tricky question is really actually in this next one, in the filtrate. And we've got, Lou, we have only like a couple of minutes, don't we?
That's right, Lisa, we do. So we can go over part B, I think. We can
Okay.
get through the rest of this, I think.
Do you think we can?
I
All right.
think you can. You're that good.
Yeah, I didn't get a whole hour. It's okay. It's okay. I can handle it. All right. So I'm going to go to a blank slide. I have a blank slide on the next page. So I'm going to have to just remember what I have for my balanced equation here, because I'm going to have some lead nitrate. I'm going to have some Ki. I'm going to make potassium nitrate, and I'm going to make some lead 2 iodide. That's the precipitate. So you should know solubility rules somewhat, and we need a balanced chemical equation. So this is what I have to begin with. And what they told me in my reaction is that I had excess lead nitrate. So when I end, I'm still going to have a whole lot of lead nitrate left over. So the potassium iodide, that's an important point right here. Okay. So the important point right here is thinking about in the filtrate, what you're going to have. Well, what is the filtrate? So the filtrate is if you've got this little funnel and then you have a beaker below it. I guess that should probably go in there. So your precipitate ends up here on your filter paper, and the filtrate is what comes through. All right. So you're dumping all the contents of that beaker out. So if you look at this filtrate, you might think, well, I just have some solid of this left over. So I make some precipitate here, but this filtrate is also going to have excess lead nitrate. So you have to think about what's actually floating around. So the yellow precipitate forms filtered, but you have excess 0.2 molar lead nitrate. So in your solution, all of the I- is gone. This is going to go down to 0. This is going to be all gone. but you are going to have this potassium nitrate and lead 2 iodide at the bottom, but the filtrate is only going to be K plus, NO3 minus, and lead 2 plus, and NO3 minus, and NO3 minus, if you're counting all that, all right? So the question is to you, in the filtrate, is the potassium concentration greater than, less than, or equal to the nitrate concentration? We call that a three-headed coin. If you don't know, just guess, like just guess at one and then try to justify. But in this case, since we have excess lead to nitrate, the K plus is going to be less than. So when you write a response, I just want to show you kind of how to write a response for something like that. So if we were looking at part C, you would say less than. And so then you say, so there's your claim. K plus is less than NO3 minus, because there is excess PB NO3 2 still in solution. So I have to have a claim, and I have to go back to and point to the evidence that was in the problem. Otherwise, I won't get all my points. So I just kind of wanted to show that to you, just to kind of show you how to do that. So we haven't finished the entire problem out, but I expect that you could probably calculate the moles of precipitate. So you would take, and I'm just going to kind of lay it out so that you can go back later. Number 5 minus number 2. That will give me the grams of the PBI2, and then you know how to change grams into moles, so that would be probably okay. And then the mass percent of I minus in the solution, now you're going to go back to those formulas on the formula sheet that were not given to you. So the percent of I minus will be equal to the grams of I minus over the grams of the tablet, which you already know, 0.425. The tricky part here is for grams of I minus. And so what you have to think about in PBI2, there are 2 moles of I minus for every 1 mole of PBI2. So that will help you get through the rest of that problem. All right. So thanks for coming. That's not all the problems. Take the handout, work through it again. I mean, the more practice that you can do, and then check your answers. Don't like look at the answers and kind of copy. Like what you need to do is like clear slate, do it, like completely close it off, and then just say, okay, I'm going to practice. I'm going to try to do all of these problems by myself. Do them all by yourself. Leave out what you can't. Time yourself. And then you're going to come back and check your answers. And then you're going to really get good at chemistry. And then you're going to love it, just like I do. So thanks for coming on a Saturday morning, getting out of bed really early. Maybe you're still in your pajamas. That would be kind of fun, right? So anyway, have a great rest of your Saturday. Thanks for coming, guys. Bye-bye.
Thank you, Lisa, and thank you, students and teachers. I'll have this posted on our Kentucky website probably by Monday, and have a great rest of the weekend and the Monday holiday. So thank you so much.
And you've stopped recording, Lou, and I don't know how to stop sharing my screen.